Hello, this is Richard Hammack's Calculus 1 course. Today, Lecture 3B, Trig Review Part B. It's our second installment of our trigonometry review. Last time in Trig Review Part A, we recalled the 6 trigonometric functions sine, cosine, secant, cosecant, tangent, and cotangent. Today, we'll begin by reviewing those 6 functions. We'll talk about how they can be used to solve triangles. We'll talk about trigonometric identities. And we'll talk about solving trigonometric equations, which are equations that have trig functions in them. From our previous lecture, we defined functions sine and cosine. These are functions of radian measure theta. For each of them, the input is a radian measure, theta, and the output can be interpreted as the side length of a certain triangle. The picture works this way. Given a radian measure theta, we move along the unit circle, theta radians, to a point P. Cosine theta is the x-coordinate of the point P. Sine theta is the y-coordinate. So cosine and sine of theta can be viewed as the side lengths of this right triangle with hypotenuse 1. Secant theta is defined to be 1 over cosine theta. The trig function cosecant theta is 1 over sine theta. Tangent theta is sine theta over cosine theta. And cotangent theta is cosine theta over sine theta. So these remaining 4 trig functions here are expressible in terms of sine and cosine. And last time we looked at examples of all of these functions. Today we move on. Now, before beginning in earnest, I'd like to talk about a couple of conventions. First of all, and you'll see this in a lot of textbooks, it's okay to write sine theta without the parentheses instead of sine theta with the parentheses. That's done a lot just to make your writing simpler and more compact. And that's perfectly fine, even if it's like writing fx for f of x, which does look a little bit strange. However, in my lectures, I'm always going to put the parentheses in, or maybe almost always. Every once in a while, if I'm really pushed for space, I might eliminate them. But I'll write our trig functions like this. And of course, the same thing goes for all of the other 5 trig functions in addition to sine. You can drop the parentheses. Other variables and expressions are okay inside of trig functions. Rather than cosine theta, we might have cosine x or cosine t. And in each of these cases, we'd interpret x or t as a radian measure since it's being plugged into a trig function. You might have something like sine of the square root of x squared plus x, and so on. That's the composition of sine with a more complex function. Now, in doing this, you have to watch out sometimes because it can lead to a slight conflict of notation. Think about writing cosine of x. Now there, x is a radian measure. So cosine of x would be got this way. You go a radian measure of x, not theta, but x to get here. And then cosine of x is the x-coordinate of that point, which is this length. Well, there x occurred in 2 contexts. It was a radian measure and it was also an x-coordinate. That may be momentarily confusing, but you quickly get used to it. After all, 2 people can have the same name and it only causes a minor confusion. In the same way, it's okay for 2 entities to be represented by the same variable. It happens a lot in math, and usually we don't even think about it. So I just want to call that to your attention. So watch out for that. We'll be using cosine of x and sine of x a lot instead of theta, because usually, let's face it, x is kind of a preferred variable in calculus. Finally, a little bit of notation. Whenever you have a trig function raised to a power, like sine of theta squared, that's almost always abbreviated as sine squared theta. So whenever you see sine squared theta, it just means sine of theta squared. Sine to the 5 of theta would mean sine of theta to the 5th, and so on. And of course, that could also be written as sine squared theta without the parentheses, as we noted up here. So we'll see this notation in action quite a bit in this class and beyond this class. Let's move on to solving triangles. I've drawn here a right triangle, and one of its angles is labeled theta. In discussing triangles where we might know an angle theta, the side that touches theta is called the adjacent side, which we abbreviate ADJ. And the side that's opposite theta, we call that opposite. And of course, the hypotenuse of the triangle is hypotenuse. We'll abbreviate that as HYP. So in solving triangles, it may happen that you have a triangle whose angle you know, and you want to find one or more of the sides adjacent, opposite, and hypotenuse. And you can always do this with similar triangles. And I'll show you the basic picture. Inside of this bigger triangle, let's put a smaller triangle that's similar to the bigger triangle, whose hypotenuse is 1. And because the hypotenuse is 1, this little triangle would fit onto the unit circle, and the vertical side is sine theta, and the horizontal side is cosine of theta. Let's look at what similar triangles say about these 6 labeled sides. First of all, think about the ratio sine of theta over 1. Sine of theta over 1 by similar triangles would be equal to opposite over hypotenuse. So similar triangles give us sine theta over 1 equals opposite over hypotenuse, and that's just sine of theta equals opposite over hypotenuse. So this gives a new geometric interpretation of sine of theta. In any right triangle, if the angle is theta, sine of that angle is going to be the ratio of opposite over hypotenuse. And because cosecant of theta is the reciprocal of sine, cosecant of theta is hypotenuse over opposite. Think now about cosine theta over 1. Cosine theta over 1 by similar triangles would be adjacent over hypotenuse. Cosine theta over 1 equals adjacent over hypotenuse, which simplifies to cosine theta equals adjacent over hypotenuse. So that's a geometric interpretation of cosine of theta. Any triangle with angle theta, any right triangle with angle theta, will be such that cosine of theta is the adjacent side length divided by the length of the hypotenuse. And secant theta is the reciprocal of cosine, so it's going to be hypotenuse over adjacent, the reciprocal of this. Now look at sine of theta over cosine of theta. With similar triangles, sine of theta over cosine would be equal to opposite over adjacent. And sine of theta over cosine of theta is tangent. So we get the equation tangent theta equals opposite over adjacent. And cotangent is the reciprocal of tangent, so it's adjacent over opposite. So in these boxed equations, we have 6 interpretations of the 6 trig functions as ratios of side lengths of triangles. And you should remember these, or more importantly, not remember them, but be able to figure them out on the spot when you need them. As an example, here's a triangle. The angle at this point is pi over 10 radians. The hypotenuse is 5, and this opposite side is labeled x. And the problem is to find x. How long is x, given the information that we have given here? Now, to figure that out, you'll notice that the side in question is the opposite, and you know the hypotenuse, and the angle is pi over 10. So opposite over hypotenuse would be x over 5. And also opposite over hypotenuse is sine of theta, which in this case is sine of pi over 10. So we get this little equation, x over 5 equals sine of pi over 10, where x is the unknown, and we can solve for that unknown simply by multiplying both sides by 5. So x equals 5 sine of pi over 10. Now, unfortunately, pi over 10 is not one of those nice angles like pi over 3 where you can figure out what sine is. It's pi over 10. We're not really familiar with that angle. And for something like this, if this were a quiz and maybe you didn't have a calculator, you'd probably just leave it like 5 sine pi over 10. But if you have a calculator available to you, you can compute sine of pi over 10 to get a decimal approximation to x. Make sure your calculator is in radian mode, because pi over 10 is a radian measure. And punch it in, multiply by 5, and you'll find that x is approximately equal to 1.545, and we've truncated the decimal places here. So it's just an approximation to, 8 decimal places. So there we go. We've solved that triangle x for the missing triangle for the missing side x. Usually in calculus we use radians, but often we'll be thinking about things in terms of degrees, because that's the way we think of angles in daily life, perhaps. And this angle pi over 10, let's see, pi is 180 degrees, and that divided by 10 would be 18. So this angle in degree measurement would be 18 degrees. And if you were thinking about this problem in terms of degrees, you'd work it out in exactly the same way, except you'd have sine of 18 rather than sine of pi over 10. And you would continue getting x by multiplying both sides by 5, and then 5 times sine of 18. Now here, what's being plugged into sine is a degree measurement. You'd have to make sure that your calculator is on degree mode, and if you work that out, you'll get exactly the same answer. Of course, your answer would be wrong if it was in radian mode. You'd be calculating the sine of 18 radians, which is not the sine of 18 degrees. So be careful about your calculator mode. As long as you're doing the correct mode, you're going to get the correct answer, whether you use degrees or radians. Let's talk more about the geometric meaning of trig functions, and on this slide I'm going to give you 3 basic pictures that really sharpen the geometric meaning of the 6 trig functions. First of all, here's the familiar picture of sine and cosine on the unit circle, and I'm going to underscore the fact that sine and cosine are really functions of radian measure theta. As you change theta, the length sine and cosine change as well. So we're going to go here and increase theta, and you see the corresponding values of sine and cosine changing as well. Now in this picture, we had a triangle whose hypotenuse was 1. If you draw triangles whose adjacent or opposite sides are 1, then you get a geometric picture of the other trig functions. For example, Think about this triangle here, where I have labeled the adjacent side as 1, so the adjacent side is 1, and then the hypotenuse and the opposite sides have different values. Let's think about the opposite side. Here's the opposite side. Opposite over adjacent is opposite over 1, so it's just equal to opposite. But also opposite over adjacent is tangent, so this opposite side in this triangle would simply be tangent of theta. Likewise, hypotenuse over adjacent is secant, but also in this particular triangle, hypotenuse over adjacent is hypotenuse over 1, so it's just hypotenuse. So the hypotenuse is secant theta. So here is a picture of a triangle whose sides are equal to secant theta and tangent of theta. And if you increase theta, tangent theta and secant theta grow, as you can see. They're functions of radian measure theta. This picture is just as fundamental as this picture for sine and cosine. And you'll find that you'll often be using this picture when you're thinking about tangent of theta and secant of theta and their relationship to one another. That'll happen a fair amount in Calculus 1, but if you go on to take Calculus 2, you'll find that you really use this picture a fair amount, fairly frequently, as well as this one. Let's see, we've got a triangle whose hypotenuse is 1, a triangle whose adjacent side is 1. Think about a triangle whose opposite side is 1. Now, in this triangle, adjacent over opposite is adjacent over 1. So that ratio is just adjacent. But also the adjacent side divided by the opposite side is cotangent. So the adjacent side of this triangle is literally cotangent of theta. And likewise, if you look at hypotenuse over adjacent, that is hypotenuse over 1, and that ratio just equals hypotenuse, the length of the hypotenuse, but also hypotenuse over 1 is cosecant. So in this triangle, we have a geometric picture of cotangent theta and cosecant theta. Given an angle theta and a triangle whose opposite side is 1, these two sides are cotangent and cosecant, as indicated. And you can imagine now if theta got to be bigger, it increased, this triangle would get shorter and shorter and shorter. Cotangent and cosecant are functions of radian measure. So we have three pictures that give geometric meanings to the function sine, cosine, tangent, secant, and cotangent, cosecant. One thing that comes from looking at pictures like this is if you use the Pythagorean theorem, this picture says that cosine of theta squared plus sine of theta squared equals 1 squared by the Pythagorean theorem. And I'm going to write that down. Sine squared theta plus cosine squared theta equals 1. You could also apply the Pythagorean theorem to this triangle, and you get 1 squared plus tangent squared theta equals secant squared theta. Tangent squared theta plus 1 equals secant squared theta. So these two equations, this one and this one, are two fundamental equations that relate the trig functions that are within them. These equations, each one holds for any value of theta. No matter what theta is, sine squared theta plus cosine squared theta is going to be equal to 1. No matter what theta is, tangent squared theta plus 1 equals secant squared theta. And there's another fundamental equation that's going to come from this triangle. Cotangent squared theta plus 1 squared equals cosecant squared theta. That's what the Pythagorean theorem says about this triangle. Cotangent squared theta plus 1 equals cosecant squared theta. That holds no matter what value theta is. There's a special name we use for these equations. They hold for all values of theta, and whenever you have an equation involving trig functions that holds for all values of theta within it, it's called a trig identity, and in the next slide we'll be looking at more trig identities. For now, let me point out that you could just replace the theta with x here, sine squared x plus cosine squared x equals 1, tangent squared x plus 1 equals secant squared x, and so on. We're going to probably move on to using x for the variables of our functions, which is a little more traditional. So let me write them this way. Trigonometric identities. Well, here are the 3 trigonometric identities from the previous slide. There are others, and on the next 2 slides, we're going to review some of the most important ones that you'll use on a daily basis, or a somewhat daily basis. First of all, think about sine of theta, and here's the picture of sine of theta on the unit circle. Here's the radian measure theta. Now, the radian measure negative theta would be flipped down on the other side of the x-axis. You just reflect this triangle across the x-axis, and here you are at negative theta. And that y-coordinate would be sine of negative theta. And look at the relationship between sine of theta and sine of negative theta. Sine of negative theta is the negative of sine of theta. And this leads to a new trigonometric identity. Sine of theta equals negative. The sine of negative theta equals negative sine of theta. That holds for any value theta. And you will often be in a position where you're working out some computation, you have sine of negative theta. It's nice to know that you can replace that with negative sine of theta. Sometimes it can simplify your expression. I mean, you might imagine that negative here canceling out with something else, another negative on the bottom or something. So this can be useful. In terms of cosine of theta is going to be the x-coordinate of this point, which is the same as the x-coordinate of this point. So from this picture, you can see that cosine of negative theta equals cosine of theta. Notice the negative just kind of disappears, and you can see why that happens based on this picture. Finally, tangent. Tangent is sine of divided by cosine. So tangent of negative theta would be sine of negative theta divided by cosine of negative theta, which would be negative sine of theta over cosine theta. That's negative tangent theta. So tangent negative theta equals negative tangent of theta. So remember these 3 identities. They can be useful. Another identity, or another set of identities, comes from the fact that at any radian measure theta, if you add 2 pi times k for an integer k, you're back to that same point on the unit circle. Add a multiple of 2 pi to theta, you get back to theta. Another 2 pi added, you get back to theta. So if you take sine of this radian measure, theta, that's the same result as if you took sine of theta plus 2 pi k. So sine of theta plus 2 pi k equals sine of theta. That's another trig identity. It holds for any theta and any integer k. Really, what we have written here is simply an algebraic statement of the fact that sine has period 2 pi. Every time you add 2 pi to theta, you get the same sign. You go around another 2 pi, you haven't changed sign. The same holds true for cosine, for the same reasons, and secant and cosecant. Also, you could say that the same result would hold for tangent and cotangent. Cotangent of theta plus 2 pi k would be cotangent of theta, and so on. However, with cotangent and tangent, things are a little bit different because at a radian measure theta, you could add not an even multiple of pi, 2 pi k, but maybe an odd multiple of pi, like just add pi down there, to get to a point on the opposite side of the circle. And notice that in this picture, let's say, let's work with tangent. Tangent is going of this theta plus 2 pi k is going to, or tangent of theta is going to be this side sine of theta divided by this side cosine of theta. And that's exactly the same as this side sine of theta plus pi divided by this one cosine of theta plus pi. So on the opposite side of the circle, you get the same triangle. The only difference is that these two sides are the negatives of these two. So in computing tangent of this angle, theta or theta plus 2 pi k, that's exactly the same as taking theta of k times pi. The negatives just cancel out. So what we get here is that tangent of theta plus pi k is simply tangent of theta. So it's a little bit different from these other four equations that we got. Tangent of theta plus pi k is the same as tangent of theta. And actually, this is an algebraic manifestation of the fact that tangent theta has period not 2 pi, but period pi. From theta, go pi times k units and add that to theta. The tangents are exactly the same. Tangent repeats itself every pi units. And the same applies to cotangent. Cotangent of theta plus pi k is equal to cotangent of theta. So read your textbook and refamiliarize yourself with these trig identities if you're a little rusty on them. We're going to move on and talk about some other trigonometric identities. You've seen in your previous classes the addition formulas for cosine and sine. If alpha and beta are any angles, then there's a formula for cosine of alpha plus beta. It turns out to be equal to cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. And I'm not going to derive that here. Its derivation it's not so bad, but it's a little complex. We're just going to take this as a fact in this course. Hopefully you've seen a derivation of this in your previous courses. There's a corresponding addition formula for sine. Sine of alpha plus beta is sine of alpha cosine of beta plus cosine of alpha sine of beta. It's a way of breaking up sine of the sum of two angles as an expression involving sine and cosine of those individual angles. And these can be useful from time to time. These identities are probably not as fundamental as sine squared theta plus cosine squared theta equals 1, but there will be places in this class where we need them. I would say you probably don't really need to remember these Whenever we need them in this course, I'm going to remind you of them, but have them on your radar. There are also what are called double angle formulas, and these give the expressions of cosine 2 times alpha. And the way to think about this, cosine 2 times alpha, that would be cosine alpha plus alpha. Just replace the beta with an alpha, and you get cosine alpha, sine alpha, minus sine alpha, sine alpha. So that's cosine squared alpha minus sine squared alpha. So this double angle formula, which gives you the cosine of the double of alpha, really just comes from the addition formula for cosine. And doing the same thing for sine, sine of alpha plus alpha, that would be sine of 2 alpha, would be sine of alpha, cosine of alpha, plus cosine of alpha, sine of alpha. And that works out to sine of 2 alpha equals 2 sine of alpha, cosine of alpha. So every once in a while, you may find that you need these. In addition, there are what are called half-angle formulas, and you can get the half-angle formulas from the double-angle formulas just by solving for the quantity that you're looking for. And I'll leave that as an exercise, but it works out this way. Cosine squared alpha is 1/2 1 plus cosine of 2 alpha. It's a basic trigonometric identity. Now, the reason it's called a half-angle formula is that if you replace the alpha here with alpha over 2, then the 2 alpha here will just be alpha, and you get an expression for cosine squared, relating cosine squared alpha over 2 to cosine of alpha, and that's a half angle right there. And that's where the name comes from. However, we're expressing them this way for a reason that I'll explain shortly. The companion to this is sine squared alpha equals 1/2 1 minus cosine of 2 alpha. And again, you may want to try it, fiddle around with these two, solve for sine squared alpha, and you'll get this expression. Now again, these two, you don't need to remember them, but they are going to be useful, and I'll remind you when we get to a point where we need them. Have them on your radar. I'll tell you one reason they're considered important. Notice that if you look at the expression for cosine squared alpha, you have a square on this side, but there's no square on the other side. And there are a lot of places in calculus where you're doing a computation and the square kind of is messing you up. You'd rather not have a square there just to make things simpler. And this equation allows you to convert a cosine squared alpha to something that doesn't have a square, which is potentially simpler. And the same for this one. So again, have all of these trig identities on this page on your radar. Maybe get a little practice with them, but don't worry too much about memorizing them. So that's it for trigonometric identities. Get some practice and read the textbook, and we'll move on. Finally, let's talk about solving trig equations. These are equations that have trigonometric functions in them. For example, tangent squared x equals 3 would be a trigonometric equation. And we're talking about solving here that trigonometric equation, tangent squared x equals 3. Now, solving for x means finding all the values of x that make this equation true. To solve trigonometric equations like this one, you're going to use all of the old techniques you have for solving trigonometric equations, along perhaps with your knowledge of the trig functions and maybe some trig identities. For this one, it's kind of like solving a quadratic, and often you can solve quadratics by factoring. You get a 0 off to one side and you try to factor and reason from that. Let's try that approach with this one. we're trying to solve tangent squared x equals 3. So let's get a 0 off to one side by subtracting the 3 from both sides. And the tangent squared x minus 3 looks a lot like a difference of two squares, doesn't it? And we should be able to factor that. And in fact, it factors like this. It's tangent of x minus root 3 times tangent of x plus root 3. Now just FOIL that out to verify that it's correct and make sure you get the tangent squared x minus 3 above. Let's see. Tangent x times tangent x is tangent squared x. Tangent x times square root of 3 minus square root of 3 times tangent x, those cancel out. And the last terms multiply as negative root 3 times positive root 3 is negative root 3 squared, or negative 3. So when you FOIL this back out, you really do get what's above. So it's a correct factoring. When we factored an equation like this, and it's equal to 0, the only way that that could be 0 is if one factor or the other factor was equal to 0. And you can consider those two possibilities separately. First of all, think about tangent x minus square root of 3 being equal to 0. For that to happen, tangent of x would have to be equal to square root of 3. For the other factor, for tangent of x plus square root of 3 to be 0, tangent of x would have to be negative square root of 3. So from here on out, we'll pursue these two possibilities separately. First of all, tangent of x equals square root of 3. What we have to do here is think about all the possible values of x that would make tangent of x equal square root of 3. And here's where it really pays off to have really worked a lot of trig values and be very familiar with the unit circle, because often you can solve these with some process of reverse engineering. You think about the unit circle and what values of x you might be familiar with for which tangent of x equals square root of 3. And one of those is pi over 3. If you work out tangent of pi over 3, you'll find that that's equal to square root of 3. So pi over 3 would be a value of x that makes tangent of that equal square root of 3. So that's going to be a solution to this equation. Now, of course, you could add multiples of 2 pi to that. Tangent of pi over 3 equals square root of 3, but any multiple of 2 pi added to that would bring you back to the same point in the unit circle, so tangent of that would also be square root of 3. But remember from a couple of slides ago, you could also add odd multiples of pi, like 4 pi over 3. Tangent of 4 pi over 3 is also equal to square root of 3. So these are two values of x, pi over 3 and 4 pi over 3, for which tangent of x equals square root of 3. So those are two solutions of the trigonometric equation that we're trying to solve. In fact, what you could do is just take this pi over 3 and add multiples of pi to it. Pi over 3 plus pi is 4 pi over 3, plus another pi, plus another pi, plus a pi again, and so on. And you're going to get infinitely many values for which tangent of that value equals square root of 3. Collecting them all together, we could say if x is equal to pi over 3 plus k pi, where k is an integer, so either here or there on the unit circle, then tangent of that number is going to be equal to square root of 3. And that's going to be a solution to this equation. So we are picking up here infinitely many solutions to this trigonometric equation, which is to be expected because after all, tangent is periodic. You'd expect to get infinitely many solutions. But we're not done yet because we've only investigated the values of x that make tangent of x equal square root of 3. Those are these values of x. Let's also look at tangent of x equals negative square root of 3. Those values of x will also be solutions to this equation. Now, from your experience with the unit circle, you'll recognize that tangent of 2 pi over 3 equals minus square root of 3. You can check that real fast. And you could also add a multiple of pi to that to get to 5 pi over 3, or just keep adding multiples of pi to 2 pi over 3, and you'll bounce back and forth between these 2 points. Wherever you are here or here, tangent of that is going to be negative square root of 3. So to summarize that, we also get x equals 2 pi over 3 plus k pi, this point plus k times pi, for any integer k. So there we go. We've solved the equation tangent squared x equals 3. Its solutions are all these values of x and all of these values of x. So infinitely many solutions. They're all the radian measures that are one of the 4 points indicated on the unit circle here. This problem indicates that it really pays off to know your way around the unit circle. If you rely too much on a calculator, then you're going to have trouble with solving a lot of trig equations. They really come from looking at the unit circle. And it takes some practice, so be sure to work lots of exercises. Sometimes in solving trig equations, the problem won't say to solve a trig equation, but to answer the problem, you'll have to solve a trigonometric equation. For example, imagine you were trying to find the domain of f of x is the function 1 over 2 sine of x minus 1. You want to find the domain of that function. So that domain would be all of the values of x for which that function is defined. And if you look at this function, it's a reciprocal 1 over 2 sine of x minus 1. You could plug in any value of x for sine, so that doesn't cause any trouble. The one thing you have to watch out for is that denominator, 2 sine of x minus 1, it could possibly be equal to 0, and that would be division by 0. So such a value of x would not be in the domain of the function. In short, we're not allowed to have 2 sine of x minus 1 equal to 0. In other words, we're not allowed to have 2 sine of x equals 1. We can't have that. Otherwise, the function's not defined. So in finding the domain, one thing you could do is, first of all, find all these values that are not allowed and say the domain is everything else. And to find those values that are not allowed, the things we can't have any x that solves this equation, 2 sine of x equals 1. So to find the domain, or everything that's not in the domain, we've got to solve this trigonometric equation. So to solve that, let's first of all divide both sides by 2. So sine of x equals 1/2. So we're looking for all the values of x that make that true. And we can figure this out by looking at the unit circle. There's one value of x that you know very well obeys sine of x equals 1/2. It's x equals pi over 6. So x equals pi over 6 is not in the domain of sine, because sine of pi over 6 is equal to 1/2. Solves this equation. But also note that if you had 5 pi over 6, sine of that is also 1/2. So 5 pi over 6 is a value of x for which sine of x equals to 1/2. So 5 pi over 6 is not going to be in the domain. Now looking at the unit circle, you can see that a radian measure at this point or a radian measure at this point is going to have sine equal to 1/2. But for any other point on the unit circle, Sine is not 1/2. And of course, you could add 2 pi k units to this point or to this point, and you're back where you started. And sine of that's going to be 1/2. So the values of x that make sine of x equal 1/2 would be x equals pi over 6 plus 2 pi k, all the values at this point on the unit circle, and also all the values at this point on the unit circle, which is 5 pi over 6 plus 2 pi k. So those are the values of x that solve this equation. So those are not in the domain of the function. So we could say the answer, the domain of this function, is all real numbers except these, except pi over 6 plus 2 pi k, and 5 pi over 6 plus 2 pi k for integer values of k. So there's our solution. So we'll just do these 2 examples of solving trig functions. Get some practice. To be honest, though, the one I chose here is maybe a slightly more complicated one than you'll find in some of your exercises. But I wanted to make sure we are working sufficiently difficult problems in lecture. So this completes our trig review. Today we've talked about the 6 trig functions, solving triangles, trig identities, and solving trig equations. All of this stuff, of course, will be used throughout calculus. We haven't even started calculus yet. We're just talking about the function review. In the next lecture, we will talk about inverse functions. That will be lecture 4 coming up. And I'll see you there. And goodbye.